Good day, everyone. I'll be discussing the next part of our topic, which focus on deformable bodies, specifically the concept of bending stress in beams. And I'll walk you through the associated formulas and sample problems. Introduction to deformable bodies. To begin, let's define what deformable bodies are. In the field of mechanics, we typically categorize objects into two broad types: rigid bodies and deformable bodies. Rigid bodies are idealized objects that do not deform under load. Think of them like solid bricks. In theory, they keep their shape no matter what. Yung mga rigid bodies ay yung mga bagay na hindi nagbabago ang hugis kahit anong force yung i-apply sa kanila. Pero theoretical lang to kasi sa totoong buhay bihira lang yung mga ganun eh. Kunyari yung sa sample ng brick walls, pag sapat na force yung in-apply sa kanila, more than sa kayang i-handle ng brick walls, usually hindi siya nagde-deform, nasisira. Para siyang yung nagkakarak. Yung isa pang type is deformable bodies. On the other hand, are materials that change shape or size when force are applied. This is a more realistic approach since in the real world, all materials deform to some extent under load, even steel. Ito yung mga bagay na nababaluktot nga, nababatak or naiiba yung hugis kapag na-apply ang force or puwersa. Kahit yung mga bakal ginagamit, nade-deform yun. Lalo kung sapat na load sapat or higit pa sa load na kayang i-handle ng material, nagkakaroon ng deformation. Okay, next, in engineering, we deal with how materials bend, stretch, twist, or compress under different types of loading. Understanding this helps engineer design safe and efficient structures like buildings, bridge, and even vehicles. Now, focus tayo sa beams. Let's narrow it down to beams, which are one of the most structural elements. Beams are horizontal members that resist vertical loads. They are crucial in all kinds of structures, from floors in buildings to the chassis of trucks. Halimbawa nito yung kahoy na sumusuporta sa kisame, yung sample ng beam. Yung kahoy nga, yung pangsuporta sa kisame. O kaya yung bakal sa ilalim ng floor ng building, yun sample ng beams. When a beam is loaded, it experiences bending, and this leads to what we call bending stress. That's the internal stress caused by the beam trying to resist deformation due to bending moment. Pag nilagyan natin ng load yung isang beam, pag sapat yung load na to, nagkakaroon to ng deformation. Ito yung tinatawag nating the bending stress. Pag inaano natin ng bending stress, the general formula we use to compute bending stress is stress equals to M times Y over I, where stress is the bending stress, M is the bending moment at the section. Ito yung epekto ng load na nagpapaikot sa beam. Then Y is the distance from the neutral axis to the outermost fiber. How far the stress is from the center. Yung I naman, yun yung moment of inertia of the cross section. Let me explain this with an analogy. Think of a ruler placed across two supports. If you press down in the middle, it bends. The top fiber fibers of the ruler are in compression while the bottom fibers are in tension. The center line where there is no stress is called neutral axis. The further you go from this axis, the higher the stress. That's why yun yung ibig sabihin ng Y dun sa formula. Yung sa neutral axis. Ito naman sa I, yung moment of inertia. This brings us to an important component. Moment of inertia, it's a geometric property that tells us how resistant a section is to bending. A larger moment of inertia means the beam can resist bending more effectively. An example is the stiffness of a shape. For a rectangular cross-section, the formula for the moment of inertia is I is equals to base height raised to 3, or base times height cube over 12, where B is base or the width, H is the height or depth. This is why tall I-beams are so efficient. Their height gives them a high moment of inertia, making them strong against bending. Now, doon naman tayo sa maximum stress. To find the maximum stress, we usually plug in the maximum bending moment and the maximum distance from the neutral axis. In a rectangular beam, this distance is just half the height. Flexural, compressive, and tensile stress. When we talk about flexural compressive stress, we're referring to the stress at the top of the beam, where it is compressed. On the other hand, flexural stress occurs at the bottom, where beam is being stretched. Interestingly, both values are numerically the same in a symmetric beam. They just act in opposite directions. So, yun lang yung sa discussion. Quick discussion sa deformable bodies. Now, punta naman tayo sa ating mga sample problems para mas lalong maintindihan. Tsaka magkaroon din ng application sa mga formulas na to. So, for our first problem, we have a problem of the simply supported wood beam in figure A is fabricated by gluing together 3 160mm by 80mm planks as shown. Calculate the max shearing stress in the glue. Based on the figure, we have a 3-layered planks which are glued together. The planks has a dimension of 160mm by 80mm stacked together, and if you multiply the height of 80mm to 3 stacks, we end up with a total height of 240mm. So our new dimension is 160mm by 240mm. We also have the figure A, which shows a wood beam under a load of 8 kilonewton meter. The load is evenly distributed. We need to solve for the reaction, which is AV and RB. We can see the A and the B. A at the left side and B at the roller side. AV and RB. We know that the beam is symmetrically loaded, and for our support, both are symmetrically supported based on the figure. To get AV and RB, we simply use summation of force vertically. Summation of force is equal to 0 upward positive. We will have AV 2 AV since AV and RB are equal. So 2 AV minus 8 times 6 equals 0. Solving the equation, we have 8 times 6 over 2. Therefore, AV is equals to RB equals 24 kilonewton, which are both upwards. Now, since we have the dimension of the support, we can solve for the moment of inertia. INA is equals to base times height cube over 12. If we substitute the value, we have a base of 160 millimeter and a height of 240 cube millimeter. And then we over it by 12, which we get a value of 184.32 times 10 raised to 6 millimeter raised to 4. Now, for the Q is equal to AY bar. The area that we are considering is 80 multiplied by 160. The A is the area, 80 times 160, which can be found with the given dimension previously in the problem statement. Now, for our Y bar, it is the distance between the center of the top plank and the center of the middle plank. The center of 80, so 80 divided by 2, we get 40. That is for the top plank. And 80 divided by 2, that is for the middle. So we get 2 40s, that totals to 80. Now, we solve for our Q. We get a value of Q is equals to 1024 times 10 raised to 3 millimeter cube. Now we have our Q, we can get our shearing stress for the glued section. To get our shearing stress for the glued section, we need the force, the shear force that we solved earlier, the 24 kilonewton. Since we need to convert kilonewton to newton, we write it as 24 times 10 cube newton, and we multiply it by our Q, which is 1024 times 10 cube millimeter cube. We over it by our solved inertia, which is 184.32 times 10 raised to 6 millimeter raised to 4. Now we multiply it by our base, which is 160 millimeter. Solving the equation, we get a unit of Newton millimeter squared. Since the millimeter cube we get at our Q will be cancelled with our 184.32, the millimeter raised to 4 here in our inertia, and there will be a leftover millimeter in our base. So we get a unit of Newton over millimeter squared. Now for the value, we get a total of 0.833 MPa. And that's how we get the shearing stress of the glued section. Sample problem number 2. This is a fundamental topic in structural engineering and mechanics of materials. Understanding it is crucial for designing safe and efficient beams in the real world. For the problem, compute the maximum flexural compressive stress and flexural tensile stress in the beam. Use beam cross-section as 300 mm times 200 mm. Based on the problem statement, our width is 200 mm and the height is 300 mm. Based on the figure, we have a maximum bending moment of 100 kilonewton meter. Our goal is to find the maximum flexural compressive stress which occurs at the top fiber and the maximum flexural tensile stress which occurs at the bottom fiber. To compute the bending stress, we have a formula of FB is equals to M over S. Looking back at our formula, FB is simply bending stress is equals to M over S. M is bending moment and S is the section modulus. Section modulus equates to I over C. I is the moment of inertia, C is the distance of neutral axis to outside surface. Now, FB is equals to M over S. We know that S is equal to I over C. We substitute S with I over C. We end up with a formula of FB, which stands for bending stress, is equals to MC over I. Since we have our base and height, we can compute the moment of inertia. We have 200 millimeter for our base and for our height 300 millimeter cube. We over it by 12, we end up with the moment of inertia is equals to 450 times 10 raised to 6 millimeter raised to 4. Now that we have our moment of inertia, we need to determine the C. To locate the neutral axis is the center. Since the beam is symmetrical, we take the height and divide it by 2. So 300 millimeter divided by 2 is equals to 150 millimeter. And we know that Rm is equals to 100 kilonewton meter based on the figure previously shown. Now we substitute our values. 100 kilonewton meter times 10 raised to 6 times the C, 150 millimeter, over 450 times 10 raised to 6 millimeter raised to 4. The given moment is 100 kilonewton meter, but since we are working in millimeter, we convert it to Newton millimeter. Now we end up with 33.333 Newton over millimeter squared. This is at the bottom part, 33.333 MPa, and this is the top part. Why are they the same? Since the beam is symmetrical, the distance C is the same for both top and the bottom. They are symmetrical, so they are equal. That is why we have the same bending stress, 33.333 MPa for both top and bottom.
Sample problem number 3. A 10-meter cantilever beam has a uniform load of 10.5 Newton meter from left to right end. Find the maximum deflection of the beam. EI is equals to 11,000 kilonewton meter squared. Given. The first thing we need to do is list down the given. The first given is the width, which is the 2.5 Newton over meter. The length of the cantilever beam is the 10 meter. EI, which is in the parenthesis, is EI is equals to 11,000 kilonewton meter squared. So The given is find the question is find the maximum deflection of the beam. The formula for the maximum deflection is deflection is equals to width times length raised to 4 over 8 times EI. So since all the given that we need is given, we just need to direct substitute it on the given formula. So 2.5 kilonewton over meter times 10 meter raised to 4 over 8 times 11,000 kilonewton meter squared. So ang lalabas na sagot natin dyan is pag 0.28409 meter or 284.0910 millimeter. And that is it for our sample problem number 3. Okay, let's proceed to our sample problem number 4. A 10-meter cantilever beam has connected load of 10 kN at the free end. Find the maximum deflection of the beam. EI is equals to 7,000 kN meter squared. Yung problem number 4 natin is halos same lang din nung sample problem number 3. Naiba lang ng konti yung given natin tsaka yung pinapahanap. So, katulad na ginawa natin sa sample problem number 3, we need to list down the given. The first given that we have is the pressure, which is the P, is the 10 kilonewton or 10,000 kilonewton. And the second one is the length of the cantilever beam, which is 10 meter or 10,000 millimeter. And the EI, which is 7,000 kilonewton meter squared. So, ang tanong is, find the maximum deflection of the beam. So, ang formula natin nun is, the elongation or the deflection ng beam is equals to P times L cube over 3 EI. So, katulad nung sa problem number 3 natin, since lahat ng kailangan nating given is given naman, that we will direct substitute it lang doon sa ating formula. So, 10,000 kilonewton times 10 meter cube is over to 3 times 7,000 kilonewton meter squared. So, yung makukuha nating elongation or ating maximum deflection ng beam is equals to 0.476190 meter or 476.1905 millimeter. And that is it for our sample problem number 4.
So for sample problem number 5, a cantilever beam 3 meters long carries a concentrated load of 35 kilonewton at its free end. The material is structural steel and the maximum bending stress is not to exceed 125 MPa. Determine the required diameter of the bar if it is circular. So first, syempre hanapin natin yung mga given para mas mapadali ang ating pagsasolve. So nakalagay dyan is yung kanyang length is equals to 3 meters. Then meron din given na force or load which is 35 kilonewtons. Then syempre meron ding flexural stress na given which is 125 megapascal. So since nakalagay dyan it's concentrated load of 35 kilonewtons at its free end. So pwede natin kunin yung maximum moment niya through this formula. M equals force times length. So syempre times natin yung 35 kilonewton sa 3 meters na length niya. So yung lalabas dyan is 105 kilonewton per meter or 105 kilonewton meter or 105 times 10 raised to 6 newton millimeter. So syempre since kung meron na tayong M, pwede natin gamitin at hanapin yung kanyang diameter. So, syempre, ang formula natin sa paghanap ng, pwede natin hanapin yung diameter gamit yung flexural stress formula. So, ayan. So, yung formula ng flexural stress is M, which is yung moment, times sa C, yung distance of the farthest fiber sa neutral axis. And then yung I is yung moment of inertia. Then yung para makuha natin yung I is equals to pi d raised to 4 over 64. So bakit ito yung ginamit natin na pagkuha ng I? Dahil ang sabi dyan, determine the required diameter of the bar if it is circular. So syempre, isalpak na natin tong mga formula na to. So ang mangyayari, alam naman natin na yung C is equals to, kapag circular is C equals to D over 2. So syempre M times 2 D over 2 over pi D, which is in diameter, raised to 4 over 64. So syempre, i-derive natin. Tataas natin yung 64, magiging 32. Then babawasan natin yung D, magiging D cube. Yan. So yon. So mangyayari dyan, yung ating flexural stress is magiging 32M over pi D cube. So ayan na, na-derive na natin siya gamit yung formula ng I tsaka nung flexural stress. So ito na rin yung magiging formula natin lagi kapag ka sinabing solid or circular. Solid yung ating given or yung kailangan hanapin. So gamit yung 32M pi d cube, mahahanap na natin ngayon ang diameter. So syempre, since sa pre-board nga kailangan naman natin is parang ano siya, so dito ginawa ko na lang is shift solve, so para mapabilis tayo. So yung flexural stress natin is equals to 32 times doon sa kanyang moment or yung maximum moment over pi d cube. So yung lalabas dyan is 204.5 millimeters. So ayun na yung ating sample problem number 5.